Today we'll be talking about thermal properties of matter. Alright, so in this chapter, the first thing we will talk about that is important is internal energy. Right, so what is internal energy? Alright, we can think of internal energy as an extension of kinetic particle model. Right, in kinetic particle model, which is 2 chapters ago, if you forget, please go and refer to that. The particles have kinetic energy due to their random motion. So all particles are in continuous random motion. As a result of their random motion, okay, they have kinetic energy. Note that this kinetic energy that we are discussing here, due to their random motion, is different from the kinetic energy due to, for example, somebody running in a straight line. Right? Somebody running in a straight line, their kinetic energy is given by half mv squared, which is what you learn in energy chapter. Right? But here the kinetic energy due to their random motion, right? Let's say of this same person that we are discussing that is running, right, has nothing to do with how fast he's running, alright, and more to do with how high his temperature is. Right, so the kinetic energy due to random motion is actually directly related to the temperature of the runner. If the temperature of the runner is high, the kinetic energy due to his random motion, right, we're talking about, for example, his skin particles, alright, will be high as well. Right, likewise, if his temperature is low somehow, then the kinetic energy due to random motion of his skin particles will be low as well. Alright, so this again has nothing to do with the, for example, running speed of a runner. Okay. Then these particles also have potential energy due to the forces between them. This is not very dissimilar from what you learn in gravitational potential energy. You realize that the Earth and any mass, alright, near the Earth will attract each other, right? And as you draw them further apart, alright, that means if an object gains height, for example, the potential energy, the gravitational potential energy increases, right? Likewise, particles also have attractive forces between them. Right, so let's say this particle attracts this particle. So in general, when these particles get further apart, right, the potential energy between them increases as well. So if you realize later on, when we'll cover the later chapters, when I go from a particle being in the solid state to the liquid state to the gas state, alright, the distance between them in general, it keeps increasing. And therefore, I would say that their potential energy increases. Right, this becomes important later on when we discuss the later parts of the chapter. Right, so our formally now defined internal energy is the energy stored that is made out of the total kinetic energy associated with the random motion of the particles. Right, remember that this energy is only associated with the temperature of the particular object in question and nothing to do with the linear speed of the object. Okay, and the total potential energy between the particles in the system. Alright, and now we want to formally cover the main points of this chapter, which is specific capacity and heat capacity. Right, so different bodies have, or objects have different capacity to store internal energy. Right, so if you look at this diagram, we can realize that number of particles matter. If I have more particles, right, then and more energy can be stored. Right, therefore larger particles tend to have larger heat capacities. Right, the nature and strength of intermolecular forces, a stiffer spring, which represents stronger force within particles, right, allows for more energy to be stored for the same extension or compression. Right. So for the same volume, solid and liquid tend to have larger heat capacities than gas. Okay. Right. Moving on, we'll move on to heat capacity. Right, is the change of its internal energy per unit change in its temperature. Right. So heat capacity can be given by capital C. Right. Heat capacity is capital C. Later we'll learn something called specific capacity, which is small c. Right. But so let's not get confused with that. Okay, so big C, which is capacity, is actually given by Q over delta theta, right? And what this essentially means is that I'll just look at a diagram here to give you an example. If I look at this iron cube, 500 gram, then I pump some amount of energy inside, 460 joules, right? And I realize that this 500 gram of iron actually raised in temperature by 2 degrees Celsius. What is the heat capacity of the object? I'll just take the amount of heat pumped into the object, which is Q, divided by the temperature change in the object, which is delta theta. Alright, so the Q is 460 divided by 2, and that will give me 230 joules per Kelvin or degree Celsius. Alright, this one you don't have to worry about difference between Kelvin and degree Celsius. For your level at this point, you just take it as the same thing. Right, there is a difference, but we won't cover it at the O levels. Right, so what this number actually means is very simple. Every time the cube takes in 230 joules of energy, its temperature raises by 1 degree Celsius. Right, anytime it loses 230 joules of energy, the temperature drops by 1 degree Celsius. Essentially, that's what it means. Right, but you realize that if For example, if my iron cube instead of being 500 grams is 1 kg, right? Clearly this number no longer applies because now I realize that I have to pump 230 joules into this block of iron to raise by 1 degree Celsius. Now if I have 2 blocks of iron of 500 grams each, clearly the heat capacity will have risen to 460 joules per Kelvin, right? You understand why, right? Because this block takes 230 joules to raise by 1 degree Celsius. If I have another block exactly the same of iron, I need another 230 joules to raise this by 1 degree Celsius. Therefore, if I look at the system as a whole, as the two bodies as one, right, because I'm interested in now a 1 kg cube of iron, right, then my heat capacity of this cube, new cube, 1 kg cube is 230 joules per Kelvin. So you can see that heat capacity doesn't really take in consideration the mass, right? And that's not very useful because if I want to compare different bodies, then I want to standardize their mass. So if I want to compare iron and water, I don't want to compare 500 grams of iron with 10 kg of water. That's a very unfair comparison because the high likelihood is that the water has more molecules because it is 10 kg of water. So it should absorb more energy, right? What I want to do is I want to standardize the mass, right? So that brings us to what we call specific capacity, which is small c, right? So remember, heat capacity is big C, specific capacity is small c. What's the relationship between small c and big C? Small c is actually big C, which we calculated over here for the 500 gram cube, divided by mass, right? And that gives me number of joules I raise for 1 gram. Let me rephrase. So the small c in this case will be 230 divided by 500 gram, which gives me 0.46 joules per gram per Kelvin, right? What this means is that if I give 1 gram, 1 gram, because this is 1 gram here, right? 1 gram of the iron cube, 0.46 joules, it will raise its temperature by 1 Kelvin. And this is a more useful comparison with water, for example, because I know here this number is for 1 gram of iron. So if I want to compare 1 gram of water, for example, then it will be a fair comparison. So specific capacity is actually more useful, right? So if I look at another calculation here, for example, now that I have specific capacity, I want to know the heat capacity of a 600 gram cube of iron. What do? I take small c multiply by the mass of this iron cube, right? Because I know this number is for 1 gram of iron. So if I have 600 grams, I just take 600 grams multiplied by this value, which is this number over here, right? So you can see straight away that small c is more useful than big C. And generally we work with small c, right? So what is small c? All right, small c is officially defined here, right? If you can read through, the formula is this one, right? Relationship between small c and big C is given here as well, right? But small c itself is c equals to q over m delta theta. Right, so we'll end this first part of the lesson